And you can use the same method for other sample statistics. So later in the chapter, you guys are going to learn about other methods, right? So like ANOVAs, regressions, chi-square, correlation, and all that stuff. So here I mapped out some of the simple statistics, which is numbers from the sample, right? That we can also use in the same methodology that we just used for averages. So for example, correlation has a correlation coefficient called R. Linear regression has a linear coefficient called R, or also a coefficient called beta, the beta coefficient, which we're all going to learn later on. The ANOVA has the eta, and chi-square has a whole bunch. All of these each one of these ones, you could use the same procedure that we're gonna do right now to derive, a sampling distribution from. So let's just show you with an example of a correlation. Okay, so we have R, which is a correlation coefficient. It goes from 0 to 1 to tell us how strong of a correlation is between two variables, right? So again, the population statistic here is grayed out. Why? Because we never know what the population statistic really is. And what is the population statistic? Let's say we have 17 million people, and out of those 17 million people, we can use this calculation that we use for our coefficient to find a number. So the number there would be 0.71. So we know that that's the real coefficient, correlation coefficient in the population, okay? Let's say we're working with, just to illustrate a little further, let's say we're working with two variables. Let's say we're working with time spent on the internet and time spent watching TV, okay? So between these two variables, there must be a coefficient, and we're assuming that the coefficient R is equal to 0.71 in the population. Here's because we're playing Jesus mode and we know everything, okay? Cool. So, but usually what we do is that we're going to draw a sample from that population of 17 million people in the Netherlands, and we're going to get a sample statistic for those 1,000 people. So based off of those 1,000 people, we're going to calculate R, and we don't do it, right? R, SPSS does that for us, so we don't have to know how to calculate R. SPSS calculates that for us. So SPSS is giving us 0.7. This is the number you see on your output, by the way, whenever you run something on SPSS. Did I say R? R is another software, but like SPSS also works. So SPSS calculates that for us. So 0.7 is the number that we get when we're running this correlation analysis between these two variables. Cool. So we found 0.7 within our sample. And then we'd have our ideal sampling distribution, which is ideally we would repeat this procedure 25 times, and eventually would get like to a normal distribution. We would be able to find a pretty accurate representation of this population statistic, of the actual R coefficient. But usually what we do is, with SPSS, we just start off with this number 0.7, which could be any number in the population, right? Which we know here because we're in Jesus mode that it's 0.71. We just plug that into our distribution as a 0.7, and then we expand that, based off of what the difference is for a sample with number 1,000. So we're like, oh, okay, sample for number 1,000 should be this width. Let's just use that to calculate the dispersion. And then you have your 95% confidence interval for your correlation coefficient. So this is what's going to happen when you're interpreting your results. You're going to be able to say, we are 95% confident that the correlation between, time spent on the internet and time spent watching TV is between 0.5, an R equals 0.5, and an R equals 0.9, with the highest likelihood for it to be an R equals 0.7. But I hope you guys understand the mechanics now of how we got to that coefficient. It's like literally very similar to what we just did with averages, except that we don't have the distributions on this side, right? And of course, this distribution here is also going to have a standard error, because the standard error is the chances that you're going to get a coefficient, of value 0.9, 0.7, of whatever of these values, whenever you draw a new sample. So when you draw a new sample, if you were to place a bet, if you're like a person who's into gambling, you should probably bet on the number 0.7, because that's the highest chance number when we draw a new sample. However, it could be that this number goes, to 0.6 or 0.8.